Hello, my name is Nora Kling. I'm a graduate student here at Kansas State University, where our recent work published in the New Journal of Physics has been carried out. In a few moments, I'll give you a quick tour of the experimental setup. But first, my colleague, Dr. M Sayler, explains the science behind our work.
In our measurements, we have explored the fragmentation of D3+ molecular ions in ultrashort intense laser pulses. In particular, we focus on experimental evidence for frustrated tunneling ionization, an exciting new phenomenon in strong field physics. In this phenomenon, a tunneling electron is captured into a Rydberg state of the parent ion. This process was first seen in 2008 by a group from Berlin who demonstrated it for helium. Subsequently, it has also been revealed in small diatomic molecules by several groups, including ourselves. Our new work is the first evidence of frustrated tunneling ionization for a polyatomic system as well as for molecular ion beams. Here we illustrate the process for D3+ using a classical simulation that we present in our paper. Near the maximum of the electric field, two electrons are ejected from the core of the molecule. Initially, the electrons are seen to oscillate in the laser field as they drift away from the deuterons, which are starting to Coulomb explode. However, one observes that one of the electrons has insufficient momentum to completely escape and is attracted by the positive charge of the deuteron. It ends up being captured into a Rydberg orbital of the deuteron and remains bound. In our paper, we present a sequence of evidence to show the existence of frustrated tunneling ionization in the strong field fragmentation of D3+.
So here we are at the James R. McDonald Laboratory, a home for AMO physics for more than 40 years, and transformed over the past decade into one of the leading centers for laser development, strong field physics, and attosecond science. At the heart of the laboratory is the Kansas light source. The laser system we use in our experiments combines the output of a conventional titanium sapphire laser with the latest in hollow core fiber pulse compression technology to deliver few-cycle, femtosecond infrared laser pulses. After we transport the laser pulses under vacuum, we interact them with a beam of D3+ ions produced from an electron-cyclotron resonance ion source. Importantly, in our setup, the laser-molecule interaction occurs in the presence of an electrostatic field that accelerates charged fragments towards the detector downstream, allowing the fragments to be distinguished from one another, as illustrated in this movie for a diatomic molecule. By coincidence detection of the fragments with a position and time-sensitive delay line detector, we perform coincidence 3D momentum imaging of all D3+ fragmentation channels simultaneously. Well, I hope you've enjoyed this brief overview of our work, and I invite you to read our paper in the New Journal of Physics to find out more.